Today we will consider three state resistors. First we will see three state switch. What is three state switch? Switch generally have two states, either it is on or it is off. Now this figure A shows a three-state switch. It consists three transistors A, B and C. Input data bit is D in and output data bit is D out, and a control signal that is enable. This enable is connected to the base of transistor A through 100 kilo ohm resistance. Emitters of transistors A and B are grounded, and at emitter of transistor C, D out, output data bit is obtained. So this is the circuit for a three-state switch using three transistors A, B and C. Three-state switch is shown in figure A. The enable input can be low or high. When it is low, when enable signal is low, base voltage of transistor A will be 0. So transistor A will be in cutoff condition. The enable input can be low or high. When it is low, when enable is low, transistor A cuts off and transistor B saturates. When enable is low, base voltage of transistor A is 0. It cuts off, it is in the cutoff condition. When transistor A is in cutoff condition, no current flow through its emitter. Then this plus 5 volt through 10 kilo ohm resistance will appear to the base of transistor B. So this transistor B will now be in the condition of saturation and emitter current through it flows. So when enable is low, transistor A is in the condition of cutoff and transistor B is in the condition of saturation. When enable is low, transistor A cuts off and transistor B saturates. This pulls the base of transistor C down to ground. When transistor A is cuts off, when enable is low, transistor A is cut off and transistor B saturates. When transistor B saturates, emitter current through it flows. Then it will make the base voltage of transistor C to 0, to that of ground. As a result, D out floats. So output bit D output, which is obtained at the emitter of transistor C, it acts like floating. So when enable is low, D out floats means this floating state is equivalent to an open switch of figure B. D out is float, it means that the circuit behaves like this switch shown in figure B. It is open switch. So when we have low enable is low, it is 0, transistor A cuts off, transistor B saturates, and base of transistor C will be grounded and D output will be floating, and the circuit behaves like this open switch of figure B. Now when enable is high, it is 1, then transistor A saturates, and when transistor A saturates, transistor B will be in the condition of cutoff, and when transistor B is in the condition of cutoff, then transistor C acts like an emitter follower, and overall circuit is equivalent to a closed switch of figure C. So this is the figure C. In this figure we see that it is a closed switch and D out is equal to D in. So we see that when enable is low, transistor A cutoffs, transistor B saturates, then base of transistor C will be grounded and D out will be floating, and the circuit behaves like a open circuit of figure B. And when enable is high, it is 1, then transistor A saturates, then transistor B will in cutoff condition, and in this case D output will be equal to D input, and the circuit behaves like a closed switch of figure C. So when enable is high, transistor A saturates, and transistor B cuts off. Now transistor C acts like an emitter follower. When transistor C acts like an emitter follower, it means that emitter follows the base, and base is connected to D in and emitter is connected to D out. So D out will be equal to D in, and the circuit behaves like a closed switch of this figure C. Table of figure D summarizes the action. This is the table D. When enable is 0, D input, we write it X. X means whatever it may be. It may be 0 or it may be 1. Then D out will be open. And when enable is 1, then D out is equal to D in. When D in is 0, D out is 0. When D in is 1, when D out is 1. Table of figure D summarizes the action. When enable is low and D in is don't care, then the out is open or floating. When enable is high, the circuit acts like a non-inverting buffer and D out equal to D in. Such switches are known as three-state switches or tri-state switches. The output can be any of the three states: low, high, and floating. So now we have three states: low, high, and floating. So this switch is known as three-state switch. Figure E shows the symbol for a three-state non-inverting buffer. This figure E shows symbol of three-state switch. We also call it three-state non-inverting buffer. Enable is control signal. When it is high active, when enable is high, it is active, means this switch behave as a closed switch and D out will be equal to D in. And when this enable is low, then this circuit will behave as floating or open switch. Figure E shows the symbol for a three-state non-inverting buffer or a three-state switch. A low enable means that the output is floating. A high enable means that the output is 0 or 1, the same as the input. This is known as normally open switch because to close it we have to apply a high enable. So this type of switch that is shown in figure E, it is known as normally open switch because normally we keep this enable 0. So it is normally open switch with enable is 0. And because to close it we have to apply a high enable. If we want to close it, we have to apply a high enable. We must keep enable equal to 1. So this is the symbol of normally open switch. Now we see normally closed switch. Figure F shows the symbol for a normally closed switch. To open it, we have to apply a high disable. This is the symbol shown in figure G, normally closed switch. Here the control signal is disable and this bubble shows that it is low active. So when disable is low, then it will act like a closed switch and D out will be equal to D in. This is shown in this table. When disable is low, the output is equal to D input, and when disable is high, that is 1, and D input is written as X, it is don't care whatever it may be, 0 or 1, the output will behave as open circuit. So this type of circuit is known as normally closed switch. Three-state buffer resistor. Buffer resistor is used to store a binary word. this is the circuit diagram for 3-state buffer resistor. We are using 4 D flip-flops, positive edge triggered D flip-flops. Clock signal is applied to all the 4 D flip-flops simultaneously, and it is positive edge triggered because of this triangle symbol. So we have 4 positive edge triggered D flip-flops. A clear signal CLR is also applied to all these 4 D flip-flops, and when this clear is 1, we have all the output bits Q3, Q2, Q1, Q0 are 0. Clear means output is 0. So this clear is high active. It means it will active when it is high. It is 1. So when clear is 1, the outputs of all the 4 D flip-flops Q3, Q2, Q1 and Q0 all are 0. And we see a control signal load, and it is also connected to a NOT gate. So we have 2 lines, one of load and other is inverted load, and we have these 4 bits x3, x2, x1, x0. These 4 bits x3, x2, x1, x0 form a binary word x3, x2, x1, x0, and we have to load this word. We have to store this word. This word will be stored when we keep this load equal to 1. We are using AND OR gates, 2 AND gates, and output of these 2 AND gates are connected to the input of OR gate. And we have 4 such AND OR gates. These AND OR gates work in this way. Then when load is 1, the right side AND gate will produce x0 in its output. When load is 1, load is connected to the input of right side AND gate, and x0 is also connected to it. So when load is 1, this x0 appears as its output, and it will goes to D0. Hence D0 becomes x0 when load is 1. And when load is 0, then its upper line, which is load bar, because it is connected to NOT gate. When load is 0, this upper line will produce 1, and this is connected to left AND gate, and the other input of this left AND gate is Q0. Q0 is connected to left AND gate, and the other input is load bar. So when load is 0, load bar is 1, then this left AND gate will be active, and it will transmit this Q0 to the input of D0. So when load is 1, D0 is equal to x0, and when load is 0, D0 is equal to Q0. And similarly, we can find for the other three D flip-flops. So when load is 1, it will load these 4 bits x3, x2, x1 and x0 to these 4 D flip-flops, and the output word Q3, Q2, Q1, Q0 will becomes this word x3, x2, x1, x0 when positive clock edge arrives. So when positive clock edge arrives and when load is 1, this binary word x3, x2, x1, x0 will be stored in this register. And if load is 0 and initially we have clear equal to 1 and all outputs are 0, initial word is 0 0 0 0, it will remains 0 0 0 0 if load is 0. When load is 1, then this input word x3, x2, x1, x0 will be stored in this register. Now we are using these 3 state switches y3, y2, y1 and y0. These are connected to the outputs of these D flip-flops, and we have a control signal that is enable. When this enable is 0, this output word will be floating, y3, y2, y1, y0 will be floating. It will act like an open circuit when enable is 0. When enable is 1, then y0 will become equal to Q0, y1 will become equal to Q1, y2 will become equal to Q2 and y3 will become equal to Q3. So when enable is 1, these switches produces the word which is Q3, Q2, Q1, Q0, and the Q3, Q1, Q2, Q1, Q0 word is equal to x3, x2, x1, x0 because load is 1. By using 3 state switches, we can convert the 2 state output of a resistor to a 3 state output. 3 state buffer resistor is shown in this figure. 3 state switches are used on the output lines. These are the 3 state switches on the output lines which produces output y3, y2, y1 and y0. When enable is low, the y outputs float. When enable is high, y outputs equal to the q outputs. Now we will see what is bus organized computers. Bus is a group of wires that transmit a binary word. Bus is a group of wires that transmit a binary word. Figure A shows a 4-bit bus. This is 4-bit bus. We have 4 wires W0, W1, W2, W3. These are 4 wires making a bus W3, W2, W1, W0. These 4 wires, we call these as bus. Bus is a group of wires that transmit a binary word. These are used in transmitting a binary word. A binary word can be transmitted by using these 4 wires. If we use 4 wires, then we can transfer a 4-bit word. If we use more wires, then we can transmit word of more bits. Figure A shows a 4-bit bus. Vertical wires W3, W2, W1, W0 form a bus. These wires are a common transmission path between the 3 state resistors. In this figure, we have these 4 3-state resistors A, B, C and D. A and B on left side, C and D on right hand side. These are 4 3-state resistors. The input data bit for resistor A come from W bus. At the same time, the 3-state output of resistor A connects back to the W bus. This is 3-state resistor A. Input data comes from W bus and output, which is a 3-state output, this also goes to this W bus. The input data bits for resistor A come from W bus. At the same time, the 3-state output of resistor A connects back to the W bus. Similarly, other resistors have their inputs and outputs connected to the W bus. So we have shown here these 4 resistors, which are 3-state resistors A, B, C and D. Input data bits for these resistors comes from this W bus and output also goes to this W bus. Output of all these 4 resistors A, B, C, D goes to W bus and input also comes from this W bus. Similarly, the other resistors have their inputs and outputs connected to the W bus. In this figure, all control signals are in uncomplemented form. These are the control signals LA, CLK, EA, and similarly for other resistors. LA is for load, A is for A resistor, L means load, LA means load A resistor. Similarly, E is for enable and EA means enable A resistor. And clock is shown by this triangle. So LA, CLK, EA, these are 3 control signals and these are in uncomplemented form. There is no bar in these 3 control signals. A load input LA to LD must be high to set up for loading. If LA is high, then this A register will be loaded by the word which appeared in W bus, which appeared in this group of 4 wires. So if we have a word on this W bus which will be loaded to A register when this LA is 1. LA 1 means load the A register, and load the A register, load by which? Load by the binary word which appears here in W bus. So to load the register A, we have to keep LA1. And similar for LB, LC and LD. A load input LA to LD must be high to set up for loading, and an enable signal EA to ED must be high to connect an output to the bus. When this enable signal is high, if EA is high, then it means that it will connect the output of A register to W bus. So when LA is high, this register A will be loaded by the word which is already in W bus, and when enable is high, EA is high, then output of this A register will appear to this W bus. Now we will see how we can transfer a binary word from one register to other register. Register transfer. How we can transfer a binary word which is stored in one register and we want to transfer it to other register. For such bus organization, it is easy to transfer a word from one register to another. The same clock signal drives all registers. If all load and enable inputs are low, the registers are isolated from the bus. If all load and enable inputs are low, these 4 registers are isolated from the W bus. Now, to transfer a word from one register to another, we have to make the appropriate control inputs high. If we want to transfer the contents of register A to the register D, then we have to make EA and LD high. If we want to transfer the word store in register A and we want to transfer it to register D, then first we will keep this EA high. Some word is stored in this register A. If we keep EA high, then this word will appear on this W bus, and this W bus is connected to this D register, and when we keep this load LD high, then the word in W bus will be loaded in this D register. Hence, we can transfer a word from register A to register D. If we want to transfer the word of register A to register D, we have to keep this EA high so that the word in A will appear on this W bus, and then we have to keep this LD high so that this word which appeared on W bus will be loaded in this D register. In this way, we can transfer any binary word from any one of the register to any of the other registers. This system of connecting the registers to a common word path is known as bus organization, which simplify the wiring and operation of computers. So this is the figure for bus organization, and it will simplifies the operation of a computer.